Welcome to ECE 302. This is lecture A2 on mean functions of a random process. I'm Professor Stanley Chen. In the previous lecture, we introduced the basic ideas of random processes. We talked about the statistical average, and we also talked about the temporal average. A very important idea to remember as we navigate through this chapter is to know what is a random process. A random process is really a function indexed by a random key. So if you recall from the previous lecture, we know that there is a function here, there's a function there. These are two different possible choices of the functions that can be drawn from a random process. These are the two realizations of a random process. By statistical average, we mean that we're going to look at the things vertically. If you look at these samples, they form the realizations of a random variable. If you look at things horizontally, you're going to take the temporal average. The difference between the statistical average and the temporal average is substantial. We will come back to this point later. But for today's lecture, we're going to look into more details of how do we actually compute the statistical average for a random process. In other words, how do we find the mean function of a random process? So let me start by defining a mean function. A mean function of a random process, x, is the expectation of this random process, x. Now, what do I mean by this expectation? Expectation over what? If you recall our statement, what is a random process? Well, a random process is a function with a random index. And therefore, when you write down this x of t, don't forget that there is a sign, there is a random key. The random key has a probability distribution, p of psi. This can be a density function if it is a continuous random variable. You can also have a summation instead of the integration if it is a discrete random variable. So when you look at this psi here, you have this PDF of the psi. All you need to do, if you try to compute the expectation, well, it would be this function multiplied with the PDF, and you integrate. That will give you the expectation of over the size. But then what? But then what is the output? Well, if you compute this, that means you have eliminated all the possible size. All these size would be gone. Why? Because you're taking the expectation, taking the average over all the possible size. Then it will become a function. This integration is a function of time t. And so that's why we call this a mean function, mu of t. Because when you integrate with respect to psi, you are going to get a function in time t. And this function is called the mean function. Let us look at a few examples to make sure that we get the idea of how to calculate the mean functions. So let's say I have a random variable a distributed uniformly in the range of 0 and 1, and then I define a random process x of t that equals to a times cosine 2 pi t. That's an extremely simple example. And then I ask you, can you find this random process mu of t? And I also want to find a particular value of mu at 0. Okay. All right, so let's just find the first one. What is mu at 0? Well, mu at 0 is the expectation of x at 0. What is the expectation of x at 0? Well, without doing any expectation, let's just calculate what is x at 0. When the time t is 0, you are evaluating this cosine at 0, right? So that is the cosine 0 here, and cosine 0 is just 1. And therefore your mean evaluated at time t equals to 0, that is equivalent to the expectation of A. Now what is the expectation of A? The expectation of A is half. So at time t0, you are getting 1/2 as your mean. That's a value because you're looking at a particular time instance at 0. But if you want to look at a general time instant t, then you're taking the expectation of over this x of t. But that's naturally not too terrible because here you have this a times cosine 2 pi t. This cosine 2 pi t has nothing random compared to the a. So this cosine 2 pi t can be pulled out from the expectation. And so now you're just taking the expectation over the a. And what is the expectation of the a? Well, just calculate that the expectation of the a is 1/2. And so you have 1/2 of cosine 2 pi t. Therefore, as I have promised, this mean function, it is a function of time t. If you plug in this time t equals to 0, you are knocking this cosine term away and you get back this constant of 1/2. So formally, how do we actually solve this problem? Now, of course, in the exam, if we ever ask a question, these will be sufficient. This slide will be sufficient for any problem. But if we want to know more about this, the formal way of doing things, or because we just defined the expectation using the PDF, and we say that there is a random index, and therefore we want to know a little bit better of how do we spell out the details in case we want to know the randomness of this random process. And in this case, we can say that this random function x of t indeed has a index sign that goes with the amplitude a, and that's given by our problem. So the amplitude has a randomness. And then if you take the expectation, you are taking the expectation over what? You are taking the expectation over psi. In other words, you're taking the expectation of your amplitude a. And therefore, I have this PDF of a. And what is the PDF of a? The PDF of a is just given by this uniform distribution, right? So a is uniform in 0 and 1, and therefore this PA of a is just 1, and 0 is if a is between 0 and 1, and then 0 and otherwise. That is your PDF. The PDF is given by this formula. It is a uniform distribution. And so you have this integration from 0 to 1. And then what? Well, and in here, that would be your x of t and a. X of t and a, that is given by your a times cosine 2 pi t. That is the function that you're looking at. And then this one here, that goes with your PDF. And then you have dA. So if you try to integrate this function, you keep the cosine 2 pi t here. Remember, you're integrating with respect to a, which is your random index. So you're integrating over the random index, and since this cosine 2 pi t has nothing to do with your a, you can pull it out, and all you have left is this a. And if you integrate a, dA, and so you will get a squared divided by 2, and you integrate, evaluate the two limits from 0 to 1, you get 1/2. You get this 1/2 times cosine 2 pi t. This is the formal way of doing the expectation, right? This should be very, very familiar to you because it is a number times a PDF, and then you integrate over all the possible state. That is the expectation. The only tricky thing here is that this expectation is not evaluated on a particular number, but is evaluated over a range of t's. But it doesn't matter, the t is the same t as here. If we replace the t by a different constant, let's say t0, you're just evaluating this expectation at t0. The rest is just to plug in the definition of your random process, and then you integrate integration, you get the exact same result as what we are getting from here. So what do we gain by doing this? you gain the understanding of the expectation. What is the expectation of a random process? You actually need to integrate with respect to your random index. And here is a pictorial illustration of what is going on. The gray curves, they represent all the possible realizations that you can draw from this function a cosine 2 pi t. They are all functions of this cosine 2 pi t, but then the amplitude is different. This amplitude is given by this random variable a, and so you have different heights. Now, what is the average? The statistical average says that I am going to look at, for example, at any time instant, I am going to put a box here, and then I treat every number as a realization of a random variable. And then I ask, what is the average? Now the average here, you can have something here, you can have something there. The average, of course, it will be somewhere in the middle, and that is 1/2. Note that this is the statistical average. This is not the temporal average. If you take the temporal average, what you're getting, you will get 1 over time t, and then you integrate from 0 to time t, and then you have cosine 2 pi t dt, and then you have a constant a here. You ignore the a because the a doesn't really matter, and then you integrate over this period of time, and of course this time t has to go to infinity because you have many cycles here. So what is the temporal average? Well, no matter how you integrate, you're covering the entire period, so the temporal average would be 0 across. This is your temporal average. The temporal average is 0. What is your statistical average? Your statistical average is here, which is the average that you compute from the vertical axis, and so you get up this point. If you go to another location, let's say you go to here, then your average is here, and therefore the temporal average does not equal to the statistical average. The temporal average is 0. The statistical average is 1/2 cosine 2 pi t. And the statistical average is a function of the time t, whereas the temporal average is not a function of time t. Let us work on another example. Here I consider a uniform distribution over the phase where I have this cosine omega t plus a theta. I want to find the mean function mu x of t. Now, as far as the homework exam goes, all you need to do is the following. You calculate the expectation of this function, which is expectation of cosine omega t plus theta, and then the randomness is theta, and so you have this cosine times this is your PDF of the theta, which is 1 over 2 pi or 0 if theta is between 0 and 2 pi or otherwise. Okay, and so now if you try to integrate this function, you're integrating this cosine function over the entire period from minus pi to pi, you get 0. Okay, so that means the mean function is actually 0 for this problem. So you ask, does it make sense? So let's look at the figure first before we go to the more formal derivation. Well, here is the set of all the possible realizations of this random process. Since if we are changing the phase, the function is going left or right by a certain amount. And then if you take the average, okay, you take the average, and by average I mean that we're taking the average vertically, or we're taking the statistical average. You ask, what is the average? Well, you get a point here, you get a point there, you get a point here, here, and here. You get all these points. The average would be 0. Okay. You go to another window. That is another random variable. You get a point here, point here, point here, point here. You get 0 again. Okay, and therefore, what is the mean function? Mu x of t, this is 0. That is the statistical average. Now, the interesting thing for this random process is that if you take the horizontal average, okay, you take the temporal average, the temporal average is also 0. Temporal average, which is the integration, that's just one period, 0 to 2 pi 1 over 2 pi, your cosine omega t plus theta dt. Now, I want to emphasize that here is the integration over time t. That is 0. The statistical average is 1 over 2 pi integration from 0 to 2 pi cosine omega t plus theta d theta. Note that here I'm integrating with respect to theta, and this 2 pi is coming from the PDF of theta. This 2 pi comes from the period, okay, for your time t. These are two different things. Although you're getting 0 for both, these are two different meanings. And therefore, if you go on and go to your homework and do an exam, if you write down this expression, you show that it is getting a 0, whereas I'm asking you for the statistical average. If you write down dt, you won't get any credit. For the reason being that these two are just completely different concepts. One is the temporal average with dt, the other one is the statistical average with respect to d theta. Alright, so now you ask, what is the more formal way of writing this expression? Well, the more formal way of understanding this is that you have this random process in x, t, and psi with this cosine omega t plus theta. And the theta is randomly indexed by this psi. And so if you take the expectation, what you are doing is that you are taking the expectation over this cosine function, and then the random index, you're taking the random index here, which here you can just take the PDF of the theta, right? So what is the PDF of the theta? The PDF of the theta is 1 over 2 pi, and therefore you get the 0, because you're integrating this cosine function for theta from minus pi to pi. That is one period, and therefore you get 0. Let us work on the third example to make sure that you really understand how to calculate the mean function. So let's say we have this discrete random process, and let this x of n equals to s to the power n. And this s is a uniformly distributed random variable from 0 to 1. So how does this xn look like? This xn is a geometric series because s is a number between 0 and 1, and so you will have a decay function. Okay, so as n grows, your s to the power n will decay. And then for different choices of s, it means that I can have s, I can have s here for a smaller s, or I can have a bigger s. Okay, it really depends on what values of s that you are choosing. Now, what is the expectation? Well, the expectation of this is the expectation of s to the power n. Okay, so now what is the expectation of s to the power n? Expectation of s to the power n is the integration of s to the power n and then ds. And so what is the range of s? Well, to be more formal, you need to put down the PDF of s, which is ps of s ds. And then this PDF of s, this thing is 0 or 1, where s is between 0 and 1, and then this is else. Okay, and so this is the definition of this expectation of this function s to the power n. And then that will give you what? That will give you 1 over n plus 1. Okay, where s is integrating from 0 to 1. So you see that this mean function mu x of n is given by this 1 over n plus 1, and that means this mean function is a decaying function, in terms of n. You can also do this more formally, right? Because the randomness goes with this s, and so you need to put a PDF of s, and that's why we come up with this formula. This is a pictorial illustration of what is going on in this example. You have all these gray lines, they represent the random realizations of this random function. The yellow one, they represent the mean function. At every time instant, for example here, you can take the statistical average, meaning that you can take the expectation over all these possible samples, and you calculate that the average is here. This is not the same as if you're calculating the thing horizontally. If you calculate the thing horizontally, you're getting the temporal average, and that's not what we're asking for the expectation. Remember, whenever you try to do the expectation, you're taking the vertical perspective, you're taking the statistical perspective. So this is the end of this lecture. We have introduced the idea of mean function, and that's a very important concept for random processes. I hope you can practice a few of these examples. Go to the ebook, and there are a couple of practice examples. Try that, and there are many homework problems on that. Please also work on it. In the next lecture, we're going to talk about the correlation between two samples on a random process. And I hope to see you next time. Thank you very much.